All right. Oh, the yes option for recording is got it. Got it. Yeah, my name's Nick. Thanks for the intro. I'm a student at the University of Victoria in Western Canada. I have a supervisor at the university. I'm in engineering. I'm not an astronomer, but you end up absorbing a fair amount through exposure to astronomers. My co-supervisor is Stephen Harrison at the DRAO facility out in White Lake, and that's where this monitor is being built. So my affiliation with the NRC is loose. It is mostly that my supervisor is employed by them, and the monitor from which I do my research is at an NRC facility. So hence the slide template, but I am at the University of Victoria. Okay, so the lion's share of the work on this project so far has been building a physical monitor. And that is, well, I'll show you that, I'll discuss that. And now we're moving into the next phase, which is kind of intelligent novelty detection is the idea. So I'll describe the monitor and I'll talk about the first steps we've begun into anomaly detection. And yeah, I don't have the chat open, so if you have questions, feel free to either interrupt me or do it at the end, whatever's normal for your seminar series. And for those that were attending the NRDZ talk earlier this week, it's a very similar presentation. I'll go over some of the machine learning parts in a little more detail, and I won't rush. The other day was a bit shorter. So yeah, I'm Nick. This is the story. Next slide. So DRAO, for those that are not familiar, is about an hour from the US border in British Columbia, Western Canada, 4 hours from Vancouver if you're driving, and has a range, hosts a range of experiments since the 60s, I think, between the 0 to 2 gigahertz range. So they also have activities. There's the 10.7 centimeter solar flux monitor, and there's a bunch of different projects varying from digital system development. There's relations to the SKA there and dish fabrication. So of interest to us as well for the rest of the talk is check out the mountains in the background of the synthesis telescope picture. They are relevant obviously to our RFI monitoring effort. So this is a bird's eye view of the site. In red are the active experiments, and you can see some of these really old experiments, the gigantic T in there, which is pretty cool. So CHIME is one of the better known experiments right now, the hydrogen mapping experiment through UBC and McGill. And what is interesting to us is our sources of RFI. We are situated between these hills. It's not fair to call them mountains, but right over those hills are a series of golf courses, an airport, there's a city to town in every direction. So we do deal with a fair amount of external interference. And a major source of interference would be, these are the main buildings. This is the disk verification area and fabrication facility, and this is the main offices. And the majority of the RFI, despite all this external stuff, the majority of the varying RFI comes from on-site. It is open to tourists, so people can come from the public to visit. Delivery drivers are often on-site. There's a sign on the neck of the road here saying turn off your cell phone, but as you can imagine, a single sign doesn't do a ton. So who cares about the RF environment / why are we doing this? We can kind of break it into these 5 sections. The first and obvious one, considering it's an astronomy observatory, is astronomers that want to have a quiet environment from which they work. Instrumentation engineers, the people actually building telescopes and while building the instrumentation on site, have to know what spec to meet and how noisy the environment is. There's people like myself and my supervisor, Stephen, who are interested in RFI detection and working in that realm, not specifically for radio astronomy, but in a way that assists radio astronomy. I think there are a few interesting applications for this avenue of research. And then there are people that actually go out and, track down people with cell phones on and leaky microwave ovens, etc. So they are interested in knowing where they have to go, tromping around, turning off people's cell phones. And finally, we have the higher level spectrum manager group, the people working towards Well, in the States, you have the National Radiodynamic Zone, and we have our own efforts through Industry Canada and whatnot here to create a quiet environment as we have a busier spectrum. So what do we want? The idea was something that monitors our entire bandwidth all of the time. So the minimum to that we figure, and we've surveyed a fair number of other RFI monitors, is groups end up with a strong spectrum analyzer, something that generates spectra, and then in theory you can look at that if you want to. So we want that real-time display capability. We want to be able to tune in and see what is actively happening on site. But further than that, we want something that actually alerts us when there are interesting events or things for us to go turn off. So that's the autonomous monitoring section. And the device that we have now is a hybrid instrument. It does use classical wideband spectrum monitoring. You know, we generate power spectra. It has some number of channels. It's all very radio astronomy sounding. That's what seems to be what's standard across sites. And then on the back end of that, we also have a software-defined radio interface. So where we can, in software, variably adjust the parameters of our monitor and deal with things like, well, this is where we're doing the machine learning part, trying to find interesting metrics beyond just occupancy plots. So this is a quick block diagram. I won't go into it in too much detail. This is what's been built. So we do have design docs on this. This is all published, the actual design of the thing. So if anyone's interested, please feel free to ask for it. We have an antenna that's all plugged in and working. It's an omnidirectional antenna operating up to, I think, 6 gigahertz. And there's signal conditioning, the DSP setup. We have observing software, which that live display I'll show you. And there is the plan to plug an API into the backend so that people can extract data live as it gets collected. And yeah, support instrumentation, instrument software. That's the story on the back end. And then yeah, this live display I've mentioned a few times. Okay, here's the actual antenna. People like to see a photo of what it is, and when you spend time waiting for the instrumentation to start working, you like to see it in built up as well. So this is the antenna that I was describing. It runs to a temperature controlled, shielded signal conditioning unit. This is all on the analog side. Support enclosure, everything's shielded. Runs in through to a, you can see the conduit along the roof there. So everything runs downstairs to this unit, which is the FPGA. And over the FPGA, we have data flowing. There are 8 10 gigabit Ethernet connections to the computer, which houses 4 GPUs where we do the software-defined side of things. So this is the unit. And now let's talk a bit about, no, I guess this very briefly first. Because one of our major sources of loud interference that's anomalous on site, maybe not fair to call that anomalous in the context of the rest of the presentation, but a loud noisy thing that comes up regularly is delivery drivers with their cell phones on, and astronomers with their cell phones on showing up to work in the morning. If you look at an occupancy plot by time, we see a huge spike in mobile phone links on site at 8 a.m. and 4 p.m. So we were overloading the receiver and trying to move it around a fair amount. So it's now been located past the edge of the roof, which is being used as a diffracting edge to create a minimum pathos requirement. Okay, so that's again just positional physical monitor. Now the digital signal processing part. So we have data flowing from the antenna into this first stage channelizer, which is an oversampled FPGA channelizer. Everything is oversampled so that we have a perfect reconstruction between channels. Each of those 16 channels is 125 megahertz wide, oversampled to 133. And it's a modification of our usual dual polarization channelizer. So instead of X and Y polarizations passing into it, we pass it even and odd samples, and at the output, here's the new and updated version. A butterfly stage allows us to use it with one polarization instead of two, but with twice the bandwidth. So from there, you have 16 channels, each representing 125, or each hosting 125 megahertz of bandwidth. And that gets passed into our GPU second stage channelizer, which is a critically sampled PFB. These are all software defined. So our targeted and current bandwidth channel spacing is 3 kilohertz, again, not oversampled. So when you plug that math through, you end up with 40,000 channels per coarse channel, per FPGA channel, and that's a total of 600,000 channels overall, ranging from 0 to 2 gigahertz. And there's no duty cycle to that, right? We're not scrolling across the spectrum. This is all, you get every sample at every time value. And those time values, our integration time is about 0.75 seconds. We have talked about lowering that, but one thing at a time. So 0.75 seconds, 600,000 channels, and there are proposals to expand a fixed slice of another few gigahertz, and then have a 1 gigahertz tunable slice, which we can shift around. And it would be the same idea for the GPU second stage, so that we can find band-specific channelization parameters. You might want to see different signal widths or different channelization shape, depending on what frequency you're observing. So yeah, again, 600,000 channels, 0.75 second cadence, and that's what we can look at and record. So this is the calibrated range of the monitor. You can see dark green bar is the calibrated range. Blue bars are current existing experiments, as well as some upcoming experiments like CHORD. The red bars are radio astronomy protected bands. So in the context of RFI monitoring, if it's in red, it should be quiet. We can expect those regions to be quiet. Another thought for flagging anomalous signals, right? If it appears in there, it shouldn't be there. Anything else on this? I don't think so. Yeah, I mean, this is just an occupancy plots and spectra at some time. Okay, so for the live display, what we currently have is a virtual machine running this interface. It is hosted on a Compute Canada cluster, and the data, every time a new integration is added to our database on the rear end, or it doesn't get added to the database, sorry. Every time a new integration comes out of the GPU, we can do science with it on site, and one version of that gets sent to this monitor, which updates in real time. This is simulated data. I built this using a Plotly front end. It's like a D3, but you actually write it in Python. It kind of seemed like a fun opportunity to learn a new tool, the new tool being Dash. I maybe wouldn't recommend it. It's not great for real-time data yet. I haven't been able to, you have to process 600,000 channels at a time and do some kind of data shading to make that work. So I'm currently updating that, doing like a WebSocket-based distributor, so that each client will be able to, they'll do their own math on their end, and everyone gets sent that same 600,000 channels. But that's kind of cool. You can scroll around, look through the spectrum, and when this is finalized, this is what those boots on the ground RFI hunters will use. So some signal appears, they can look at this quickly, scroll around, see what's active. This cloud instance is another way that we can disseminate data. If we have some rolling buffer of data products and people care for it, they can download it directly. So speaking of data products, yeah, so the integrated spectra, that's the classic, the cadence I talked of, 3.3 kilohertz spacing. Store that for about a week, which will cost us about 5 terabytes of space in a rolling buffer. The idea here is that if you are an astronomer and you run some experiment, it's up to you to download your RFI data afterwards, and then you can do whatever science you want on that. So you can get the rawest version of that data from us. We'll also do calibrated min, average, max, and an occupancy plot a few times daily. And the idea behind that is to create over time, create an image of our RF environment evolution. So is our site becoming more occupied? You know, are we having an increasing problem in these cellular ranges? How much is Starlink a problem, et cetera? So that's the other item, and that isn't a ton of data, so no reason to plan on getting rid of that yet. And we're looking at long-term trends, so we'll store it all. And lastly, the idea is on the intelligent detection side is to store bounding boxes and create feature vectors for the RF environment. So for independent individual signals as well as the environment as a whole, and then be storing that as long. We have to figure out exactly what we're storing, and then from there we can decide if we're going to keep it forever or not. And we have a kind of a project, a grant active right now on creating a way of distributing RF environment information between sites so that you can compare different sites, compare different RFI environments, etc. And that's where this last piece falls in as well. You can just pass around integrated spectra all you want, but someone has to look at it. And our understanding of surveying the scene and DRAO's experience as well is you can have a great monitor, but nobody's affording someone to just stare at a screen all day of scrolling waterfall plots. So you need a more intelligent way of disseminating this information. So we have integrated spectra, we have a live monitor. At this point, we match, and I think it's fair to say exceed a standard RFI monitor, just considering our bandwidth and cadence. How do we improve upon it? And this is what we're starting to step into. I think a perfect system will not alert you to everything. An ideal system would just tell you when something is novel and interesting. This signal on site is not meant to be here. Or this signal that we have received, you could turn it off. Like those are the ideal flags that someone gets, right? It's like, oh, the microwave oven is leaking. Like how explicitly can you pass along this information? And in terms of identifying novelties or things that can be dealt with on site, there are two ways of doing this. And one of those ways would be to find absolutely everything, store feature vectors for absolutely everything. And then you have this wealth of data that you can identify novelties within. So with the plan of post-processing and with the plan of returning to these data sets later on. And the second approach is to only find triggering events. So can you real time on the air only identify things that you care about? Because the cell phone tower next door is always on. So do you really want to save a never-ending bounding box describing where that signal is? In pursuit of the first approach, we had the opportunity, I'm not sure if Nathan West is on this call, but he and DeepSig hosted a data competition for the SPOC 2021 conference on eval AI, which we were able to use as an opportunity to develop some tools. So the story for this competition was they delivered, I see a chat. Sorry, I just was looking at my back end screen. Is there anything there I should concern about? I can't find it. We'll worry about that later. Okay, so the story for the conference. They distributed a simulated data set of several hundred files. Inside of each file was a wideband recording of containing anywhere from 0 to hundreds of signals. So these are 3 example files. You can see on the left, this is one signal is in the file, not consuming much bandwidth. The second one has a bunch, and the third has a lot of little signals. And the task was to say, can you detect them and can you classify them? There were, I think, 15 known modulation classes. It's, again, all synthetic. It was a great way to build these tools there, and we've tried transfer learning since then. But I think one of our next steps as well is to enhance this data set a bit and try and create a more dynamic background environment. So in terms of, I'll show you how I did it in a second, but the red boxes here are my predicted bounding boxes, and the white boxes are the ground truth. So we have a pretty close match. And when we do an intersection over union between the labeled data set and the predicted data set, it was performing quite well. Again, that sounds arbitrary, but I don't remember the exact score. Okay, so the approach that I took is you take some, you turn this wideband recording into a waterfall plot. You split that into overlapping tiles. just for the sake of convenience, I did 50% overlapping tiles, but in an actual implementation, we would drop that as far as we could afford to. A 50% overlap, you can see between the, if you can see my mouse, this is time0, time1, and with a 50% overlap, this is the same signal within it. So it's easy to not miss signals, and you give every chunk of every signal 2 chances to be discovered. So probably overkill, but easy to implement the first time around. Tile it, overlapping both in frequency and in time. You'll note that these 2 channels, this is F0 and F2. This is kind of demonstrative. It's not an actual, these were not next to each other. But the reason I said F0 and F2 was that F1 would contain half of this square and half of this square. So you would see a tile in between them. Each of these files in the data set came with the bounding box annotations relative to the entire file. So you had the bandwidth and the time duration and the start time and the center frequency. So you split the waterfall into tiles, and then you figure out what part of what bounding boxes are in each of those tiles, and you make it a relative coordinate. So each of these will be a bounding box, a labeled bounding box from 0 to 1 and from 0 to 1, and then a relative X and a relative Y dimension to that bounding box. You train on that. This was a YOLO architecture. Joseph Redman published it a bunch of years ago. You only look once. It's quite fast. And it's also a classifier. So it's been designed to do things like detect the difference between dogs and horses and whatnot. And so you pass it bounding boxes, and then you say what class it is. And while between some modulation classes, you are able to just look at a waterfall plot and say, you know, this is AM or this is FM. And I think that's an interesting next step as well, is to pass it the classes and see how well it performs. Even if it sorts out 2 or 3 of the classes, you remove the need for a later classification stage. You say, oh, if it's AM and FM, don't bother plugging that into your classifier. But otherwise it would just be an unknown or one of the many classes that get merged together. So for this, I said, call everything a blob, and you have every bounding box independent of class is a blob. So at the end, it only had to learn square boxes. It's a pretty easy thing to do. We had we have an implementation of this that is essentially linear. It's a 2D filter that does the same bounding box YOLO-based detection through a YOLO architecture. So then when you're testing and evaluating, you normalize all the predicted bounding boxes and the tiles to where they exist in coordinate space, in time frequency space, and then you check the intersection over union between every 2 boxes. And if it exists at all, you merge them. Another interesting piece there is if you have the intersection over union value, you can tell when 2 squares barely overlap. And that's another trigger we can use to say these are actually 2 separate signals. But we didn't have that in this data set. All of the signals were independent in both time and frequency. They weren't overlapping. So IOU greater than 0, it's one thing. And now moving away from the competition a little bit, for the competition, we just did a naive digital down converter where each signal is brought down to baseband, and it was classified using a ResNet classifier that was hyper performative. It was really impressive for identifying those 16 classes. It's harder to plug that into our real data set because we have more than 15 classes, and I worry that that just becomes a decision tree where what classes do you train it on? And we don't want to do machine learning for the sake of doing machine learning. We want to improve upon what can be done otherwise. And there are existing discrete tools that will answer the modulation question. So maybe we'll end up down this ResNet architecture path, but maybe we will just plug it into a tool that says this is, you know, QAM64 or whatever. And now that's the story of the competition. Outside the story of the competition, this method is all the same, but for the down conversion, we do a more intelligent on-air down conversion. We can't afford, we have a huge bandwidth. We can't afford to store everything. We can't afford to naively, in terms of computation power, down convert every signal that we find to baseband and then store all of those, time series. So what we have to do is do a on-air live time down conversion and then extract whatever information we want, and then throw away that data, right? We're saving integrated spectra, and that's consuming 5 terabytes a week. We're not going to save thousands and thousands of time series every week. So every day. So to do that, what we have is an oversampled PFB. It's the story of synthesis filter banks and reconstruction filters. So we have a 2 times oversampled filter, polyphase filter that divides the entire input spectrum into smaller channels. We have the entire input spectrum get fed into this YOLO detector, and that says, oh, there's a bounding box here that consumes 2 or 3 channels. And those 2 or 3 channels are passed into a perfect reconstruction synthesis filter bank, which then reconstruct that baseband time series. And from that, we can extract interesting information. The real value to this is that rather than naively, shifting every signal through the entire spectrum to 0, filtering, etc., you can do all of the signals, do the first stage together through that PFB, and then through the second stage, we're trying to figure out a smarter way of plugging all of those synthesis filters into a single FFT. And then in theory, you can move them all to baseband at the same time as well. So that's an active piece. I think I'm going to be talking about this part, the DDC part, at RFI 2022. I think I'm remembering that right. Okay, so taking the, we're getting there. Sorry, it's been 20 minutes or so. Actually, how long do I have, Daniel? Sorry, I don't actually know how long I meant to talk for.
The slot is nominally until the top of the hour, but I think we end at the hour, so you've got some time. But usually there's about 10 or 15 minutes of questions as well.
Yeah, no problem. Okay, just making sure I wasn't over time.
Yeah, no problem, not at all.
All right. So now talking about transfer learning from the simulated data set into the real world. I'm not sure how high the contrast is on your screens, but there is a ripple all the way across, which you could see in that original calibrated range plot as well. So that combined with just the nature of noise in reality is that we don't have a perfect noise floor. Despite that, we thought we already have this model trained on the synthetic data set. Can we just apply it directly to our real data set? And the answer is yes. The question that raises is the YOLO architecture returns a bounding box with a confidence, and it says we are, in this case, 95% confidence that there's a blob inside of this box. And now we have to pick what confidence to use, right? And if you're seeing a theme here, it's that I'm not a fan of decision trees. I don't really want to pick the confidence that's best. So that's a downside to this method that we're trying to sort out. For the purposes of the competition, we were able to pick a confidence based on a calculated F1 score, which is the classification combined with the intersection over union of the boxes. But in reality, we don't know what is true. You don't want to trigger on nothing, but you also don't want to miss signals. And at 95% confidence, you can see we miss a bunch. So decrease it, 75% confidence, where are the signals? 50, 25. And now we can see it's picked up all these little signals scattered between, but it's missed a few. And I think it's missed this big one, although I don't think that's true because we see it on the next slide. Point being, it's imperfect without having been trained with some kind of a matching dynamic background. There are thoughts for how to handle these signals that it's missing. And one direction to take this in is to do bounding box identification using our detector, but on a kertogram, which should ignore background noise levels. I'm not sure. I mean, that's just a whole bunch more computation that's required versus just enhancing our model to train on variable background noise levels. So I think the first step there will be to expand our model. Okay, what does that actually look like when we look at samples of the data? It works, again, we don't have a metric because we don't have a ground truth data set for real life, but this one's pretty good. It's the duration of the file. The bounding box has outlined it perfectly in both time and frequency. No complaints there. Versus this, and maybe not entirely a big red sad face, but it is a question mark. And the question mark, well, the sad face is that it didn't grab the very start and very end of the signal, right? You can see it overlapping the bounding box. But these are 10-second signals separated by 20 seconds of silence. And if it had found these perfectly, it would have represented, it would have 2 bounding boxes. But that raises another question that says, are they not the same signal? Do you want to downconvert each of these separately, or is this one big on-off signal? So again, we kind of head down the realm of decision trees, and that's probably the next big step here. Okay, so there are other ways to do object detection. Obviously, YOLO is not the only way. There are UNet architectures, and there are these like pixel objectness directions. This is often called segmentation in the image analysis or image analysis world. This is interesting in that it's also relatively class agnostic. So you can train it on, here it's lines and snakes, and then it will execute relatively well on chess pieces and Civil War reenactment scenes. But at the end of it, what you end up with is a pixel by pixel mask. And I think there's an argument here that says, or a pixel mask saying this is foreground and this is background. And I think there's an argument here that says, is that better than just running the whole thing through kurtosis, where you end up with a pixel mask of your spectrum anyway, right? Saying this is statistically noise and this is statistically not. So there are interesting pieces here. I think the really interesting piece is that the snake is hard to see, right? That's a more complicated foreground to background differentiator than signal in Gaussian background. So it's performing well. I'm just not a huge fan of the pixel mask idea. All right, so that was the detect everything and downconvert plan. And what I'm currently working on is trying to see, is there a better way to only find triggering events? So while this pixel objectness is often called segmentation, when I speak of this type of segmentation, I don't mean that. What I mean is this method, and it's old, it's been improved upon, I'm sure. They pass in a whole bunch of images, and it is unsupervisedly able to detect the difference between multiple foregrounds and a background. And the way it does that is by segmenting the images into chunks and comparing across the data set. And it says that in our architecture, the foreground is defined as that which is common across all of the images, but uncommon with respect to the image you are looking at. So there are kids in a whole bunch of different images. So kids are common across this data set, but they're always standing in front of different stuff. So with respect to the actual image, the kid is rare. With respect to the data set, the kid is common. Therefore, that is a foreground. And it identifies those foregrounds, and it says the complement of the foregrounds we find in your image is the background. Now, what's interesting to me here is, can we reverse this idea and say, when we look at our dynamic radio environment, full bandwidth, not individual tiles, we have a relatively common background, not just noise ripples and whatnot, but the signals that are always on. And they are common across the entire data set of waterfalls that we look at, both in, in intensity, any characteristic you really care to look at, but also positionally. And is it possible to say, learn that? And that is what's common across all images. It is, and everything that is not common across those images is anomalous. So the complement of the background is the foreground in that sense. And that's what I'm trying to plug in right now. And I was working on it yesterday and hope to have some photos for you, but I don't. So that's the idea anyway, is can we learn the dynamic radio environment, including the signals that are common, and claim everything that is the complement of that commonality is an exciting signal. So that's kind of the story. An issue with these approaches, all of them so far, perhaps except the bounding box like YOLO detector, is that it doesn't accommodate any kind of an active learning feedback loop. So if you have this, the common classifiers we've looked at, the foreground, background, co-segmentation, inversion problem, if it starts to ignore a certain chunk of the spectrum, and we're looking at that and visually seeing that there are signals here you should be caring about, how do we ask it to please care about that? So that's one thing we're pursuing right now. And lastly, the image size. I mean, we have a 600,000 by 1 pixel image come out every 0.75 seconds, and we need context with the last however many seconds to do that in. So, to assess, right? We need context. So you end up with a huge repetition rate, like a huge, you're looking at the same data a lot. And how do we minimize that best? That's the story. I think that's my last slide. And that's where we're at so far. As you can see, we're just at the start of this like novelty detection and the intelligent monitoring phase. I'm happy to show you when we've got more results for you, but that's it.